In this problem, we're asked to find the difference in pressure between the points 1, 2, and 4 and 4. So basically 1 is your x-coordinate, 2 would be your y-coordinate, and likewise for the other one except for we have 4 and 4. And that's going to be if the fluid is water and elevation changes are negligible. Now we're also given this velocity potential, which is phi. That's given as negative 3x squared y minus y cubed. And again, x and y are just the x and y coordinate locations. Now, first thing we need to recognize is if the flow can be described by a velocity potential, that already tells us that we've got irrotational flow. So we already know that we have irrotational flow. That's going to be important to realize. Alright, so that means if we have irrotational flow and we're looking between 2 points, that we can use Bernoulli's equation. Alright, so that's going to be an important thing to pay attention to. Now, let's write down Bernoulli's equation. We've got P1, where that's pressure, at point 1 over density, plus V1 squared over 2, plus gravity times Z1, where Z would be elevation. And that's going to equal P2, which is pressure at point 2, over density, plus V2 squared over 2, plus GZ2, where that would be elevation at point 2. Now let's go ahead and cancel out some of this stuff. It tells us that elevation changes are negligible, so that means we can get rid of the g times z terms since we're not paying attention to elevation. And that's going to leave us with pressure and velocity. And density we can find because we know we're dealing with water. Now, next thing we need to do, we want the pressure difference, so we need to find a difference between P1 and P2. That's what we're looking for. Alright, so that's what we're searching for. So in order to find that, we need to next get our velocities. So this velocity right here, that's going to be the magnitude of velocity at point 1. This V2 is the magnitude of velocity at point 2. So let's find those next. Alright, so we need velocity. And we can get our components of velocity using the velocity potential. We know that u, which is the x component of velocity, is equal to the partial of phi with respect to x. Now if we look back up here at phi, if we take the partial of this equation with respect to x, we end up getting negative 6xy. Alright, and we'll use that in just a second. Next, let's find v. So v will be the y component of velocity. That's going to be equal to the partial of phi with respect to y. Now again, if we look back up here, that'll give us negative 3x squared minus 3y cubed, 3y squared. Alright, so now we have that. So now we have two equations for the velocity components, and we know the coordinates of each of our points. So let's look at the first point. So 1 and 2. So x will equal 1 here, y equals 2. Essentially we'll take these values and plug them into the equations we have for u and v. So u in this case is going to be negative 6 times 1 times 2, which is negative 12. This is feet per second. V is going to be negative 3 times 1 squared minus 3 times 2 squared. And that, if you notice, is going to be 9 feet per second. Right? Now we have our two components for the velocity at point 1. Now we need the magnitude. So the magnitude then, let's just call it V1. And if we look up here, you can see that this is V1 squared. So let's go ahead and write the squared of this. So V1 squared is going to be u squared plus v squared. So we can just plug in our numbers, and we'll get that V1 squared is 12 squared plus 9 squared. and that's 225 feet per second. Let's do the same thing for V2. So for V2, we'll be at a different point. We'll have x equal to 4 and y equal to 4. Let's find u and v. U will be negative 6 times 4 times 4, and that gives us negative 96. V is negative 3 times 4 squared plus 3 times 4 squared. Now if you notice, these terms are going to cancel, so that goes to 0. So our v2 squared then will just be u squared plus v squared again. This time we'll just have 96 squared, which ends up being 9,216 feet per second. Right. So there's the square of the magnitude of velocity at point 2. Now we can take those velocities and plug them into Bernoulli's equation, and then we'll be able to get what we need. So we've got our P1 over density. Density will be 1.94 for water, plus the 225 over 2. 225 came from this right here, V2, and that's got to equal the pressure at point 2 over density, which is 1.94, plus V2 squared, which is 9216 over 2. Now we want the pressure difference, so let's bring the pressure terms onto one side, everything else to the other. So I'm going to say that P1 over 1.94 minus P2 over 1.94 is equal to 9216 over 2 minus 225 over 2. And from there you should be able to solve. So we got P1 minus P2, that's going to equal 8,721.27, and that's pounds per square foot. Now we wanted to find it in PSI, so let's convert over. So we'll multiply that by feet squared divided by 144 inches squared. And that results in 60.56 psi. So that gives us the pressure difference between those 2 points. And we found that using the velocity potential right here. So the key to this problem is realizing that if you can describe a flow with phi, that we have irrotational flow, which allows you to use Bernoulli's equation.